10.3 marks the beginning of probability. So probability is a measure of how likely something is to happen, or how unlikely it is to happen. And so when we're dealing with this, in this lesson, we're going to look a lot at rolling dice and drawing cards off of a deck of cards, because these are things that most people are familiar with. They're good examples for learning about probability. So if we're looking at a six-sided die, something like this, there's six possible outcomes. So when we roll this, there's six things that could happen. We could roll a 1, a 2, a 3, 4, 5, or a 6. Each one of these is called an event. So an event is a specific thing that can happen when you do some action, roll a dice or roll a die, or draw something off a deck of cards. So rolling a 5 would be an event, or drawing an ace of spades, or we could even do something that would have more than one outcome, so like rolling an even number, so that would be a 2, a 4, or a 6. We could say that's an event as well. And when we're talking about the probability of an event, we're always going to have a number from 0 to 1. So this number will describe how likely or unlikely it is for something to happen. So we've got numbers all the way from 0 to 1. Probability of 0 means that it absolutely will not happen. It is impossible for this thing to happen. Probability of 1 means that it absolutely will happen, that there's no way that thing could not happen. Probability of 1/2 is halfway between, so that means it's equally as likely for that thing to happen as it is not to happen. And then you can imagine if we're to the right of 1/2, between 1/2 and 1, say 0.75 or 3/4, that's something that's more likely to happen than it is not to happen. Something over here, say 0.25 or 1/4, that would be something that is more likely not to happen than it is to happen. Now we're going to be looking at two types of probability in this lesson: theoretical probability and experimental probability. We're going to start with theoretical probability. So this is, in theory, what we should expect to see when we roll a die, or do whatever thing that we're talking about. So how we calculate probability, theoretical probability, is going to be that we're going to take the total number of possible outcomes, the total number of things that could happen, and put that on the bottom of the fraction. And then on the top of the fraction goes the number of ways that we can have what we're looking for to happen. So if our event, say, is rolling a 4, we take the total number of ways that we can roll a 4, which, if we're on a standard six-sided die, there's one side that's a 4, so that's 1. Out of the total possible things that could happen, there's 6 things that could happen. We could roll a 1, 2, 3, 4, 5, or 6. So we take the total number of things that we're looking for, which is rolling a 4, there's only one way for that to happen, divided by the total possible number of things that could happen. Part B of example 1, rolling an even number. Well, there are 3 even numbers on a die. There's 2, 4, or 6. So there's 3 ways to roll an even number, so that's going to be 3 out of the possible 6. And then we could reduce that fraction to 1/2. Part C, rolling an 8. Well, normal dice only go up to 6. There's no 8. So there's no possible way to get an 8. So we could say that there's 0 ways to get an 8 out of the total possible 6. Well, 0 out of 6, that's just 0. So remember, probability of 0, that means it's impossible for that thing to happen. So it is impossible to get an 8, so that's a probability of 0. It's not going to happen. And part D, not rolling a 2. Well, there are 5 ways to not roll a 2. We could roll a 1, a 3, 4, 5, or 6. So 5 ways to not roll a 2, so that's 5 out of 6. Let's go on to ones about a deck of cards. So if we want to know the probability of drawing a red card, now again in this lesson I'm assuming that you know what the contents of a deck of cards are. If you don't, or if you've forgotten, go watch that video I made that describes the contents of a deck of cards, because you need to know that for this lesson. So the probability of drawing a red card, well, we're going to take the number of red cards that there are. So there's the red cards are diamonds and hearts. Each of those has 13 in them. That's 26 cards out of the deck. So 26 of the 52 cards are red, and so the probability of drawing a red card is 26 out of 52, and we can reduce that to 1/2. We could have looked at this a couple different ways too. We could have said, well, half of the cards are red, half of the cards are black, so we could have gotten to it just there. So red is one of the 2 colors that there are. Or we could have even looked at the 4 suits. We could have said that 2 of the suits are red out of the possible 4 suits. Reduce that fraction, you end up at 1/2 either way. All right, part B, probability of drawing an ace. Well, remember that there's 1 of each suit. For each card, there's 1 of each suit, so there's 4 aces in the deck, so that's going to be 4 out of 52. Well, 4 out of 52 we can reduce to 1 out of 13, so 1/13 is the probability of drawing an ace. Part C, drawing a colored card. Well, every card has a color on it. They're all either red or black, so that means there's 52 out of the 52 cards that are colored. 52 out of 52, that's 1. So the probability of drawing a colored card is 1. So no matter what card you draw, you're going to draw a card that has some color on it, either red or black. So you will always draw a colored card. All right, probability of drawing the 8 of spades. Well, there's only 1 of those. So remember, there's 4 8s and there's 13 spades, but there's only 1 card that is both an 8 and a spade. So there's only 1 8 of spades. So that's 1 out of the 52 cards. All right, example 3. A community center hosts a talent contest for local musicians. The order in which the 7 musicians perform is randomly selected. What is the probability that they will perform in alphabetical order by their names? So if we think about how many ways there are to arrange things in alphabetical order, well, there's only one. It's alphabetical order. That's the only way to arrange things in alphabetical order, is just having them in alphabetical order. So there's one way to have them in alphabetical order out of the total possible number of ways to arrange them. Well, think back to 10.1, where we learned how to count up the number of ways to arrange some number of objects. So if we have 7 objects, 7 musicians, there's going to be 7 factorial different ways to arrange those musicians. So that's going to be 1 out of 5040. So 7 factorial, that's 7 times 6 times 5 times 4, all the way down to 1. We get 5040. So that is the probability. Now we're going to look at odds. So odds is very similar to probability, but instead of comparing the total number of ways to get what we want out of the total possible number of things that could happen, we're going to be looking at the number of outcomes we're looking for, and then divide that by the number of outcomes we're not looking for. So it's essentially the same, except instead of dividing by all the possible outcomes, we're going to be dividing by the number of ways to not get what we're looking for. So let's just jump right into an example. Example 4, determine the odds for a 20-sided die. So this is a die that has 20 sides on it. So the odds in favor of rolling a 5, now I skipped over odds against, we'll get back to that in just a moment. But odds in favor of rolling a 5, so we're going to take all the number of ways that there is to get a 5, so there's one way to get a 5. And then out of the number of ways not to get a 5, that's on the bottom. So there's 19 ways not to get a 5. So the odds in favor of rolling a 5 is going to be 1 out of 19. Now for odds against, this is essentially the same thing, except we're going to be flipping it around. So it's just the reciprocal, actually, of the odds in favor. So we have 19 ways to not get a 5, and 1 way to get a 5, so the odds against rolling a 5 are 19 to 1. Part C, odds in favor of rolling a prime number. Okay, well we're going to have to figure out which ones of these of 1 through 20 are prime numbers. So again, prime numbers are numbers that can only be divided by themselves and 1. Now 1 is not prime, doesn't count as a prime number. 2 is the smallest prime number. So 2 is prime, 3 is prime. Now 4 can be divided by 2, so it's not prime, but 5 is prime. 6 can be divided by 2 and 3, so it's not prime, but 7 is prime. 8 can be divided by 2 and 4, so it's not prime. 9 can be divided by 3, so it's not prime. 10 can be divided by 2 and 5. 11 is prime. 12 can be divided by 2, 3, 4, and 6, so it's not prime. 11, 12, so 13 is prime. 14 is not prime. 15 is, 15 is not prime. Can be divided by 3 and 5. 16 is not prime, but 17 is prime. 18 is not prime, and 19 is prime, and 20 is not prime. So these are all the prime numbers up to 20. So there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So the odds in favor of rolling a prime number, well, there's 8 possible prime numbers. And then we're going to divide that by the number of numbers that are not prime. So if there's 8 prime numbers from 1 to 20, that means there's 12 that are not prime. And we can reduce that fraction to 2, let's see, divide by 4, we get 3. So 2 out of 3. So the odds in favor of rolling a prime number are 2 to 3. Odds against rolling a prime number, we just take the reciprocal, flip that over. The odds against rolling a prime number are going to be 3 to 2. Okay, now let's get to experimental probability. So theoretical probability was just in theory. Before we actually do anything, we can expect that some outcome is going to happen. That's what theoretical probability is about. Experimental probability is you actually roll a dice and see what the actual numbers are, see what actually happens. So it's different than theoretical probability in that we're taking real things that have happened and calculating the probability based on what actually happened rather than what we should expect to happen. So we're going to roll a die 6 times and we're going to record what happens. So we're going to take this die, roll it. There we got a 4. Okay, we're going to roll again. That time we got a 3. And we'll roll again. Now we got a 2. 3 more times. There's a 4. And we'll roll again. There's a 6. So that's 5 times, 1 more time. And we get a 6 again. Okay, so I just rolled that die. 6 times. The numbers that I got were 2, 3, 4, 4, 6, and 6. So you can see that this is different than theoretical probability because with a theoretical probability we should expect if we roll the die 6 times we should expect to get 1 once, we should expect to get 2 once, we should expect to get 3 once, 4 once, 5 once, and 6 once, but that didn't happen. I got 6 twice, I got 4 twice, and I didn't get 5 and I didn't get 1. Okay, so what's the experimental probability of rolling 2? Well, we got a 2 once out of the 6 times that I rolled it, so that's 1 out of 6. So actually this matches the experimental probability. So rolling a 2 in this specific experiment happened to be the same as the theoretical probability. We rolled a 2 once, which is what we should have expected. Part B, though, says what's the experimental probability of rolling a 4? Well, I rolled a 4 twice, so I got 2 out of the 6 rolls were a 4. So 2 out of 6, that's 1/3. So 1/3 of the rolls I had were 4s. But the theoretical probability tells me that I should have only 1 out of the 6 times. So this is different. The experimental probability here is different than the theoretical probability. So again, experimental probability is based on what actually happened in an experiment as opposed to theoretical probability, which is what we should expect to happen in theory. Last bit here is geometric probability. So this is geometric because we're dealing with areas here. So we're playing darts with a dartboard that has a radius of 25 centimeters. So the radius is the distance from the center, from the bullseye to the edge, 25. And then the bullseye has a radius of 1 centimeter. Assuming that you hit the dartboard and that all places on the dartboard are equally likely to be hit, what is the probability of hitting the bullseye? So this is a little bit of a not real situation because of course you can miss, and of course if you're aiming, you're probably going to be aiming for the bullseye, so the probability that you're going to hit any place on the dartboard is not going to be the same. But this is a theoretical experiment here, so we're just going to take it at face value. So we're assuming that any place on the dartboard is equally likely to be hit, and we're assuming that we will actually hit the dartboard as well. Okay, so the probability of then hitting this circle, this bullseye that has a radius of 1, well, if we take all the ways that we can get what we want, which is all the area of this circle, and divide it by the area of the entire thing, that will give us the geometric probability. So again, probability, we take what we're looking for divided by all the possible outcomes. So what we're looking for is the area of this circle, which if it has a radius of 1, area of a circle is pi times r squared. So for radius of 1, we get pi times 1 squared. Then we divide that by the area of the big circle, which if it has a radius of 25, that's going to be pi times 25 squared. And then we can reduce this. Well, pi divided by pi, that just goes away. And then we get 1 over, and then 25 squared is 625. So we get 1 out of 625. That's the probability of hitting the bullseye.